It's fall, so nobody's on the river, which is a good thing. There's something wonderful and satisfying about throwing rocks into the water below. Gravity takes over, slowly at first, and then more rapidly and inevitably to the water, and then down to the Earth's surface below the water. The first and most foundational of all of Newton's laws is his universal law of gravity. About 50 years before Newton, Galileo did work on what would later be called gravity. Galileo was one of the first to realize that objects pick up speed at a constant rate as they fall. In other words, things accelerated. He also observed that, excluding air resistance, objects with different weights fell at the same rate and hit the ground at the same time, even if one of the falling objects was traveling horizontal to the ground. In other words, if you fire a bullet from a rifle that is even with the ground and drop a bullet at the same time from the same height, they will hit the ground at exactly the same time. The downward pull works independently from the horizontal speed. You can even demonstrate this. Place one coin at the edge of a table and another coin that you will flick off with your finger. Drop the coin and flick the other at the same time, and they will hit the ground together. By the way, there is a very popular story that Galileo went up into the Leaning Tower of Pisa in Italy and dropped off two cannonballs of different weights. They hit the ground at the same time, thus disproving the old Aristotle theory that objects with different masses would fall at different speeds. But did it really happen? It seems to be a popular trend to discredit traditional stories like this, but the source of this incident comes from a biography written by one of Galileo's own students named Vincenzo Viviani. He stated that Galileo actually performed the experiment. Newton added to Galileo's works by mathematically describing gravity as a togetherness force, a universal attracting force that all objects possess. Newton's actual math formula looked like this. F is proportional to m1 times m2 divided by the distance between them squared. Distance is often showed as d squared or sometimes r squared. And it's a bit complicated, but I think you will get the basic idea of what Newton was getting at. F is the force of gravity, and it is directly proportional to all this over here. The mass of two objects, mass 1 and mass 2, are multiplied together. Then you figure the distance from the center of the one to the center of the other, and you square the distance. Divide that distance into the mass, and that gives you a number, which is the force of attraction between those two objects. So, according to Newton, gravity depends on two things: the mass of the objects and the distance between them. If I increase the mass of this one, they will be more attracted to each other. And then the distance. If I bring the objects closer together, they're going to be more attracted again. And if I bring them further apart, they're going to be less attracted. That's pretty much Newton's law of universal gravitation. Now, the two objects, M1 and M2, could be any two objects in the universe. The Earth and an apple, the Earth and the moon, the Earth and the sun, you and the rubber duck on your desk. Gravity exists between any two objects in the universe. So if the rubber duck and you have gravitational attraction, why doesn't the duck fly off your desk into your face? That's because the force between you and the duck is very, very tiny. 100 years after Newton, Henry Cavendish built a device that accurately measured the force of attraction between two objects, an amazing feat way back in 1798, especially as the gravitational attraction between small objects is almost impossible to detect. But Cavendish did it, and it not only allowed him to accurately weigh the Earth, but he was able to refine Newton's original formula by adding in a tiny but important constant into the formula. That constant is 6.67 times 10 to the minus 11th power. And these numbers here are Cavendish's units that he used, meters and kilograms and so on. This tiny, tiny number, minus to the 11th power, is called the gravitational constant, nicknamed ironically Big G, and it refined Newton's original statement into this precise formula. F equals G times M1 times M2 divided by the distance squared. After you plug in the mass of you and the mass of the rubber duck, you will find that the gravity between you and the duck is so utterly small you never feel it. It takes a massive, huge object like the Earth or the moon to really make gravity easily measurable. In fact, if you plug in the mass of the Earth into one of these M's, say M2, and do the math, you will discover that the acceleration of gravity on Earth is actually 9.8 meters per second per second. This equation of Newton's gave scientists a mathematical formula for why the planets move around the solar system, and it revolutionized how people thought about the structure of the universe. Newton's universal law of gravity does not describe how the Earth attracts rocks to the ground. It describes the gravitational attraction that both objects have to each other. The Earth attracts the rock, and the rock attracts the Earth. Of course, the Earth is way, way more massive than the rock, so the rock moves way easier than the Earth does. Things that weigh more are harder to get moving than things that weigh less. But there is an equal tug between the tiny rock and the Earth, nonetheless. Now, weight and mass are not the same, but for nearly everything you and I do here on Earth, they are virtually identical. Mass is a measurement of how much stuff is in the object, how much matter. Weight is a measure of how much gravity is pulling on that stuff. Imagine you are standing on a scale and we can slowly turn Earth's gravity down. As I turn the dial down, gravity pulls less and less on you and registers less and less weight. But you haven't suddenly lost mass or parts of yourself. You have the same amount of stuff in you as always. But gravity is not attracting you as much, so you weigh less. Now, if we turn it up again, the mass of Earth begins adding its gravitational attraction to you, and the scale registers more weight on it. Incidentally, we could turn your personal gravity off just as well, and you would start weighing less again. Newton's equation says regardless of which object is more massive, you simply multiply the masses of the two objects together to get the force of gravity. Everything attracts everything else in Newton's universal gravitation law. The hard thing to understand about Newton's gravity is not so much that everything in the room is attracted to everything else, although that is weird. The hard thing to understand is the mouse and the elephant. A mouse and an elephant jump off the tallest building in Cartoon World at the same time. You have somehow removed all of the air resistance as if they were inside a very clear box. Will the elephant fall faster than the mouse? Well, your intuition says, of course, he's heavier. He's an elephant. But reality says something else entirely. Newton's law of gravity says they fall at the same rate and hit the ground at the exact same time. And they really do. Gravity pulls more on heavier objects and less on less massive objects. Let me say that again. Gravity is actually pulling harder on the elephant than it is on the light mouse, yet they are both falling at the same speed. And why is this? Well, let's see if we can work through this idea. Let's say we have a 1 pound weight over here, and gravity will, of course, pull on it with a certain amount, with what we will call 1 gravity force. Now, if you put a 2nd pound over here, gravity will likewise pull on that pound also. Now, if you have 3 of the 1 pound objects over here and weld them together, gravity pulls equally on each of the 1 pound objects, but since you have welded them together, it pulls the group with 3 gravity forces. That's easy enough. But at this point, most people assume that since gravity is pulling harder on the welded unit, it will fall faster. But it won't, because even though the more massive thing has more gravity pulling it, because there's more mass, it resists moving 3 times as much as the 1 unit thing over here. The lighter thing resists less and has less gravity to get it moving. The more massive thing resists more with more gravity pulling it. It becomes a perfect balance with those 2 things happening at the same time. 1, where gravity pulls with different amounts depending on how much mass the object has, and 2, where the objects themselves resist moving. The more mass of the thing, the more they don't want to move very quickly. The end result is that everything falls on this planet at about 9.8 meters per second regardless of their mass. Elephant and mouse, each resisting by different amounts, the elephant resisting more, and each getting pulled by gravity with different amounts, means they both fall at the same speed and arrive at the ground at the exact same time. You can largely demonstrate this to yourself even with air resistance in the way. Two rocks of different sizes will fall and hit the ground at the same time. As we said, this is the fall season and nobody is on the river, something you need to be certain of when doing a gravity experiment like this. Two rocks with different masses. Now, we say that things fall at 9.8 meters per second, but the actual acceleration is 9.8 meters per second per second. And what does that mean? If you were a car traveling 5 miles per hour per second, it means that you start at 0 and in the first second you go 5 miles an hour. By the next you are going 10 miles an hour, 15 miles per hour in the third second, 20 miles per hour in the fourth. When you jump out of an airplane, your personal gravitational field, as weak as it is, exerts a tug on the Earth, moving it ever so microscopically toward your meager mass. The Earth, on the other hand, is way more massive and is attracting you toward its massive gravity as well. You fall at 9.8 meters per second, and you will continue at that rate, but not forever. Because you are skydiving through a sea of air, and the air is trying to get out of your way, but eventually it cannot move fast enough. It is exerting a pressure on you against your downward increasing speed. Eventually, there is a limit where the air drag balances against any further possible speed increase, and you have hit your top speed, your terminal speed, often called your terminal velocity. Falling people hit terminal speed at about 54 meters per second or 121 miles per hour. We can prove that objects fall at an increasing speed with our rock off of this bridge. The rock takes just over 1 second, or 30 frames of video, to hit the water. So we will stop the film at every 10 frames, or about every 1/3 of a second. And you can easily see that at each stop, the rock is increasing its speed and falling further. Every second, everything falls faster than the second before until it reaches its terminal velocity. In Newton's day, they were constantly throwing things off of tall buildings or down ramps to figure all this out. One of the problems they kept having was air resistance. It was always messing with the experiment, so it was difficult to prove. But there's nothing like doing an experiment like this in a place where there is no air resistance to test the idea. And that is exactly what the astronaut David Scott did during the 4th moon landing.
Beautiful picture, Dave. Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Here's a question. If everything pulls on everything else with its own gravitational force, then why does a helium balloon go up when you let it go? Does it defy gravity? No, nothing defies gravity. It comes with the package of having mass, whether you are a grape or an asteroid. So why does the helium balloon go up, seeming to defy gravity? Well, we live in this atmosphere full of air. The air is a fluid. We are like fish living in the water, unaware that we are submerged in a fluid. We are so literally immersed inside a sea of gases that we don't think we are inside of anything at all. But we walk around inside an ocean of air every day. Just wave your hand around and you can feel it. If you are underwater and you blow bubbles, are you surprised when they float up? Do you feel like the bubbles are somehow defying gravity? Well, it is the same thing with the helium balloon. Less dense things float in more dense things. The air bubble is less dense than the water around it, and the helium gas is less dense than the atmospheric gas surrounding it, so they float up. Okay, so they both float up, but why do they float up? Because the pressure at the bottom of the bubble is slightly more than the pressure at the top of the bubble. That is the actual physics, the force that causes them to go up. There is more pressure at the bottom of a swimming pool or the ocean because of all the water stacked on top of it. And there is more pressure on the surface of the earth because of all the air stacked on top of it. This creates a column from more pressure to less pressure. And even though it is very small, there is more pressure at the bottom of a balloon than at the top. As a result, the pressure squeezes the balloon from the bottom up, pinching it up, chasing it upward in the water or the air. We call it buoyancy and say that the bubble floats to the top, when in fact it is getting pinched all the way up and out. The helium balloon does not defy gravity, but it overcomes the downward force of gravity as it gets pressure pinched all the way up into the thinner and thinner air sitting above it. At this point, it's important to stop and make a rather peculiar observation. We observe that things with mass are attracted to each other, especially us to this planet, and we give this attraction a name, gravity. We call it this because a person who is grave is very serious and thoughtful, literally heavy with thoughts. We say, he's a rather grave person. In fact, it is likely that it was Newton himself that coined this word to describe this force, gravity. But then, after mathematically describing how it works on bodies, Newton said in the Principia that he had absolutely no idea why objects have gravity, or virtually anything else about gravity other than it exists. In other words, Newton could describe what was happening, but he was completely clueless as to why it was happening or what was causing gravity. And today, we are still equally clueless as to what causes gravity or how it fits with our modern theories of physics. 300 years after Newton, this man, Albert Einstein, developed a very different view of what causes gravity, and we will explore his ideas in a later segment. But even after Einstein, modern science is still almost in the exact same place as Newton. We can describe the effects and make mathematical equations for predicting the effects, but the cause of gravity is still one of the greatest mysteries in all of physics. So here are some questions to test if we are understanding Newton's universal law of gravity. Question number 1. Yes or no? The elephant and the mouse each have the same amount of gravity pulling on them. No, they do not have the same amount of gravity pulling on them. Gravity pulls more on more massive objects. Just consider you. To move the elephant and the mouse, would you pull equally on each one? No, you pull way harder on the elephant because he weighs more, and you pull less on the mouse because he has less mass. You pull the elephant a lot and he moves 10 feet. You pull the mouse a little and he moves 10 feet. Gravity works the same. Question number 2. Yes or no? The elephant experiences a greater force of gravity, yet both the elephant and the mouse fall at the same speed. True. The more massive object resists more because it has more mass. It is lazier and doesn't want to move. We refer to this resistance, this laziness, by a special name which we will reveal in the next segment. Question 3. Yes or no? Gravity stops where the atmosphere stops. No. Newton's force of Earth gravity extends to the moon and beyond. In fact, the moon has no atmosphere, and the moon definitely has gravity because the moon has mass. Question 4. Yes or no? Astronauts experience zero gravity in space. No. Astronauts experience very powerful gravity, but as they fall, they are also moving forward very fast. This constant falling gives the appearance of zero gravity, but there is probably no such thing as zero gravity anywhere, an idea that we will look at closely in the next 2 segments. And our final question, number 5, yes or no? Newton mathematically described gravity. Yes. Newton did not invent gravity. He mathematically described it as a real force that affects all objects with mass. Through his work, we have been able to accurately predict the movement of objects in the universe, like rockets and cannonballs, the moon, and the planets. Your weight is the force of gravity acting on your mass. As you are sitting there listening to this, I want you to actually feel your weight in the chair and feel the weight as you're sitting on the floor. That weight is the force of the Earth's gravity acting on you and your gravity acting on the Earth. We all weigh something different when we step on a scale because our masses are different, and gravity pulls more on more massive objects. When gravity pulls this rock into the water, it plunges into the river. But if the moon and the Earth are also being attracted to each other, why don't they slam into each other as well? Well, the answer to that question brings us to our next segment and to the first of Sir Isaac Newton's laws of motion.